Welcome back. We finished up last time talking about atomic mass, but I failed to mention one kind of important thing. Let's take another peek at our periodic table. When you look at this periodic table, we talked before about how you can find the atomic number. On this particular one, they're up in this little left-hand corner. Phosphorus is 15, chlorine 17, etc., etc. But you will also notice that there is a decimal, or mostly decimal number, down at the bottom. And again, it's on different places in different periodic tables. But this number right down here is the average atomic mass. So in the last problem, we were calculating copper's average atomic mass. Well, what do you know? There it is. So you have to remember that's not the mass number. The mass number is protons plus neutrons. There's a bunch of different mass numbers. Okay, for oxygen, there's actually oxygen 15, oxygen 16. There's carbon 12, there's carbon 14. This number is the average, which is based on the abundance. So most of the time, when I ask you, okay, what's the average atomic mass of calcium, you can look at the periodic table, you can find it. What's the average atomic mass of iodine? As long as you can find iodine, you can find the average atomic mass. But today I'm going to get a little tricky, and I'm going to say what's the average atomic mass of water. Yeah, small problem here. Is water on the periodic table? No, but it's ridiculously easy to find. All you have to do is know the formula. Okay, formula for water is H2O. That means that water is made of 2 hydrogens and 1 oxygen. Okay, 2 hydrogens, and this is understood to be a 1 oxygen. So if we want to find the atomic mass of water, we just have to add up the parts. Okay, each hydrogen, 1.008. Oxygen, 15.999. Add all that up, you get the average atomic mass. Now, let's have a real quick discussion about these decimals. As a general rule, of course, you're better off using exactly what's on the periodic table. However, in many of the things that we do in chemistry, okay, we don't use the thousandths place or past that. Our equipment doesn't measure to that. We don't use it. So, if you have something like hydrogen, which is 1.008, okay, 1.0 something, it is okay to actually say it has an atomic mass of 1. For oxygen, 15.999. It is perfectly fine to say that has an atomic mass of 16. Okay, and you'll see these differences in rounding throughout the semester, but the big thing I need you guys to know is the only time you can make it a whole number is if it is a 0.0 something or a 0.9. Sodium, 22.990. You can say it has an atomic mass of 23. That's fine. Okay. If we looked at, let's see, what's a good one here? If we look at carbon, carbon has 12.011. You can make that an atomic mass of 12. But when they don't have 0.0 or 0.9 something, don't mess with it. Okay. If I ask you the atomic mass for boron, it's 10.811. You cannot make that into an 11. So leave it the way it is. Tenths will mess up our data because our equipment does measure in tenths. But when you get down to the hundredths, you're generally safe rounding. All right, so let's move on to the topic of the day. The topic of the day is actually another number problem. Most samples that we have do not have 4 atoms in them, okay, or 1, or 12, or let's be honest, even 150. Okay, most of the ones we have a lot of atoms. I mean times 10 to the something. So we don't want to deal with those ginormous numbers. Okay, we want things to be simple. So scientists actually created a brand new unit. Okay, and they made this unit simply to make our math easier. The new unit is called the mole. Dun dun dun. I would draw one if I could, but you know that I can't. A mole is defined as exactly the number of atoms, okay, whoa, how's that for a misspelling right there? Atoms in exactly 12 grams of carbon-12. Why do we use carbon-12? Most common thing around anyway. It's easier. So this is literally a man-made unit. We defined the mole as this is the number of atoms that are in 12 grams, like 12.00000 grams of carbon-12. And it was a guy named Avogadro that did this research. So he decided that the number of atoms in 12 grams of carbon-12 was going to be called Avogadro's number. And that Avogadro's number, the number of atoms in 12 grams of carbon-12, is actually going to be how many particles are in 1 mole of an element. Okay? So what he did is he said that 1 mole is equal to 6.022 times 10 to the 23rd atoms. Okay? Now that can be atoms, that can be molecules, that can be particles, that can be pieces. There's a lot of different words you can use. But basically, he said 1 mole of anything is 6.022 times 10 to the 23rd pieces. We call them formula units, and that's a term that you will probably see more as the year goes on, formula units. So the comparison I use is a dozen, okay? Most of you guys know that if you have a dozen, you have how many? 12. So if I say you have a dozen bicycles, how many bicycles do you have? 12. If I say that you have a dozen keychains, how many keychains do you have? 12. If you have a dozen iPhones, how many do you have? 12. If you have a dozen pens, how many do you have? 12. If you have a dozen friends, how many do you have? 12. Okay, you see where this is going. If you have a dozen of anything, doesn't matter what it is, you got 12. Avogadro's number works the same way. If you have a mole of anything, you have 6.022 times 10 to the 23rd. That's how many of that thing you have. So if you have a mole of carbon, you have 6.022 times 10 to the 23rd carbon atoms. If you have a mole of water, you have 6.022 times 10 to the 23rd molecules of water. Hey, if you have a mole of iPhones, God bless you, you can make some money. You have 6.022 times 10 to the 23rd iPhones. Take that out of scientific notation, that's a big number. If you got a mole of pennies, you have 6.022 times 10 to the 23rd pennies, and you need to share with your teacher. Just kidding. The point is that just like having a dozen means you have 12, having a mole means you have 6.022 times 10 to the 23rd. Yes, you have to memorize that number. So what we're going to do with that number is back to dimensional analysis. Yay! Okay, we are going to learn that 1 mole, okay, of anything is equal to 6.022 times 10 to the 23rd. And again, atoms, molecules, particles. So let's say I tell you you have 0.3 moles of fluorine. And I want to know how many atoms that is. We can calculate it. So we're going to set up our cross like we learned how to do before. Okay, top left is always my given, 0.3 moles of fluorine. Bottom right, always the unit I'm getting rid of, moles of fluorine. Top right is always the unit that I'm looking for, okay, atoms of fluorine. And now my conversion factor is right here. So I know 1 mole is 6.022 times 10 to the 23rd atoms. Plug it in my handy-dandy calculator, get my answer. I don't have one in front of me, I'm sorry. The other thing we can do is take things one step farther and look at something called the molar mass. Okay? The molar mass is exactly what it sounds like. It's the mass of 1 mole. Just because you have the same number of something doesn't mean they have the same mass. Okay? Imagine, oh, it's drawing time. This is me. Yay! Let me put a big old smile on my face. Woohoo! Okay? In this hand over here, I have a dozen eggs. 4, 5, 6, 7, 8, 9, 10, 11, 12. Don't even ask me how I'm holding them, just go with it. That is 12 eggs. Okay? In this hand over here, I have a dozen elephants, which now I'm very terrified that I have to try to draw. So there's the big old body, there's 4 legs, stop judging me, floppy ears, there's the trunk. Okay, I don't know what happened to that trunk, let me fix it. There's the... Dude, okay, that's my elephant. Alright, but now pretend I have 12 of them. So, you know, I'm just going to go like this and you'll never know the difference. So look, it's 12 elephants, yay! See, look, I'm drawing every single one of them. Can't you tell? Can't you see these amazing drawings? Okay, whatever. So in that hand, I have 12 elephants. 12 eggs, 12 elephants. Do I have the same number? Why, yes, I do. There are 12 over here. There are 12 over here. Do they have the same mass? No. this arm is now broken for the rest of my life because I was just holding 12 elephants. And I am no longer smiling, Miss Michael. Now I am frowning and crying in pain. Okay? So we don't have to have the same mass. Same is true with atoms. Just because you have a mole of copper doesn't mean it's the same as a mole of carbon. Yes, you have the same amount, but you don't have the same mass. So the cool thing about the way Avogadro did this is the molar mass of any atom is actually the same as the atomic mass. Because he defined a mole as exactly the number of atoms in 12 grams of carbon-12, it works out where the protons and the neutrons basically get a value of 1. So if we look at the periodic table again, you can see there's an average atomic mass. So if I want to know the molar mass of nitrogen, well, what do you know? The molar mass of nitrogen is 14.007. That means 1 mole of nitrogen is equal to 14.007 grams. Okay, that's the mass of it. That's the way the mole was created. It's actually really helpful. If I want to know the mass of 1 mole of iron, 1 mole of iron, still the same number of particles, is 55.933 grams. Okay, so it's pretty nifty, and we can use it as a conversion factor. So let's say I have 3.5 moles of copper, and I want to know how many grams that is. Okay, again, set up my cross. 3.5 moles of copper, grams of copper. Okay, and now I've got to plug in my conversion factor. So this time, I got to go to my periodic table. I'm looking up copper. Okay, copper's right here. So I can see that 1 mole of copper is 63.546. So 1 mole of copper is 63.546 grams. Do my math, do my calculations, these cancel, and that gives me my molar mass as a conversion factor. If you're feeling squirrely, you could even go one step farther, okay? So we know 1 mole, 6.022 times 10 to the 23rd atoms, pieces, particles, molecules, whatever. We also know that 1 mole is equal to the mass in grams off the periodic table, and that varies by element. So let's say I ask you, dun dun dun, you have 3 grams of copper. How many atoms is that? Well, this time when I set up my conversion, I've got to kind of think this through. Okay, I got to say, okay, I have 3 grams of copper, so this is grams of copper, this is atoms of copper. Now, you got a couple different options here. Option 1 is look at your factors up here. Okay, 1 mole is 6.022 times 10 to the 23rd atoms. 1 mole is equal to the grams off the periodic table. Well, if both of these two things are equal to 1 mole, that means they're equal to each other. So I could actually go ahead and say, okay, I'm going to put 6.022 times 10 to the 23rd atoms on the top, and then I'm going to go to my periodic table, look up copper, and it's 63.546 grams. How did I know those two can be put on top? Because they are both equal to 1 mole, therefore they are equal to each other. My other option, if that's just not the way your brain works, is I can do this as a 2-step conversion. I can say, okay, I can't go straight from grams of copper to atoms of copper because I don't have anything that says grams and atoms. So I can use mole as my middleman. And mole is the ultimate middleman. So I can say 1 mole, 63.546 grams. And that gets rid of my grams. Then I can say moles of copper to atoms of copper. Get rid of my moles. 1 mole, 6.022 times 10 to the 23rd. There is no difference in setting it up this way and setting it up the way we did before. This way, you've got a 1 here. Change colors. You got a 1 here and a 1 here. The way we did it before, we just kind of squished it all together. So it's really about what works in your mind. Okay? So take your time, practice this, think this through. This really is a huge key to what we're going to be doing in chemistry.